In this example, we're asked to find the real zeros of a polynomial function, and the function that we're given does not factor using our traditional methods. So the first thing that we're going to want to do is find the list of potential rational zeros, which is also sometimes called the P over Q list. Remember, P is the constant and Q is the leading coefficient. So we start with all the factors of P, which are plus or minus 1, plus or minus 5, plus or minus 7, and plus or minus 35. And then we look at all the factors of Q, which are plus or minus 1 and plus or minus 2. From these, we can create the P over Q list, which is all possible combinations of a factor of P over a factor of Q. We begin in an organized way by starting with the first factor of Q and writing every factor of P over that first factor of Q. So that's 1 over 1, which is plus or minus 1, 5 over 1, 7 over 1, and 35 over 1, which is plus or minus 35. Once we've written all the factors of P over the first factor of Q, we move over to the next factor of Q. So 1 over 2 is plus or minus 1 half, 5 over 2 is plus or minus 5 halves, 7 over 2 is plus or minus 7 halves, and 35 over 2 is plus or minus 35 halves. So this completes our list of potential rational zeros. Now we're going to cross-reference this list with the graph of the polynomial. And that'll tell us which one of these potential zeros appears to also be an x-intercept on the graph. So let's come over here to our graphing calculator and put in the polynomial function. And when we come over to the graph, it's kind of hard to see what's going on here. We're looking to see which of the values in this P over Q list appears to also be an x-intercept. Now, it looks like we could have an x-intercept here at -5, and -5 is in our P over Q list, but these values are a little bit iffy. They don't appear to be exactly on the integers. So now we're going to begin testing for zeros, using only good candidates that are both in the list of potential rational zeros, but also appear to be x-intercepts on the graph. So we'll start with testing x is equal to -5. If x is equal to -5 is a zero, then that means x plus 5 will be a factor of our original polynomial f at x. If x plus 5 is a factor of f at x, that means that x plus 5 divides evenly into f at x. And if x plus 5 divides evenly into f at x, that means that if we treat this as the divisor and f at x as the dividend, x plus 5 divides into it with a remainder of 0. So we're going to use division to test to determine whether or not -5 actually is a 0. And synthetic division is what we're going to use because this divisor is linear. We open up our backwards L box and we're going to put the 0 of the divisor into this box, which is -5. The 0 of the divisor is also the 0 that we're testing. And now we're going to put the coefficients of the dividend to the right of the box, and our original polynomial function is the dividend. So 2 is the coefficient on x to the 4th, 11 is the coefficient on x cubed, -5 is the coefficient on x squared, -43 is the coefficient on x, and 35 is the constant. So we draw a line here, leaving a lane of space for some work, and we begin our synthetic division. We start by bringing down that leading coefficient, which is 2, and then multiply on the diagonal. -5 times 2 is -10, and then we combine down. 11 combined with -10 is +1. We multiply on the diagonal to get -5, and again we combine down to get -10. We multiply on the diagonal, which gives us +50. That product is written under the next coefficient. And then we combine down, -43 combined with 50 is +7. We multiply on the diagonal, -5 times 7 is -35. And when we combine down, we get a remainder of 0. When the remainder is 0, it confirms that x plus 5 does divide evenly into the polynomial, which means that x plus 5 is a factor of that original polynomial function. When this happens, we should pause with the synthetic division and begin the factorization of our polynomial. So now we can start to begin and factor the original polynomial. We know that x plus 5 was a factor. that can be pulled out of the original polynomial. What remains after we divide out an x plus 5 is going to be the quotient that we gained right here. Now we started with a 4th degree polynomial and we just divided out a 1st degree linear factor, so this quotient is going to be a 3rd degree expression. That means that this 2 is the leading coefficient on the x to the 3rd power term. 1 is the coefficient on x squared, so we'll just write plus x squared. Negative 10 is the coefficient on x, and 7 is going to be the constant. So essentially what we're doing is we're using the P over Q list and cross-referencing that with the x-intercepts to try to find good candidates that will help us to factor this polynomial. Now, we've already started this factorization, but we're still not done. We need to factor it as much as possible to get all the zeros. Remember, we're actually expecting 4 zeros because this is a 4th degree polynomial function. So we need to repeat this process, go back to our P over Q list, and cross-reference that with the graph. This x-intercept does not appear to be exactly on negative 3, and negative 3 is also not in the P over Q list, so that makes this not a good candidate. Let's move over into this region. We could zoom in on this, but it also appears to be happening at positive 1, and positive 1 is in our list, so I think that's what I'd like to test next. So now we're going to test to see whether or not x is equal to 1 is a 0. If x is equal to 1 is a 0, then x minus 1 will be a factor of f of x, which means that x minus 1 will divide evenly into that f of x. If x minus 1 is a factor of f of x, it must also be a factor of this polynomial because this one is the only one that's going to factor any more. X plus 5 is linear and therefore prime. So any remaining factors must be a factor of this quotient, which means that we would continue our synthetic division, but this time using the 0 of the divisor, but dividing into the quotient to continue with the factoring process. So we leave a lane of space here for our work and then bring down that 2. We multiply on the diagonal and that product comes up under the next coefficient. Combine down, we get 1 plus 2 is 3. Multiply on the diagonal and that product comes up here under the next coefficient. Combine down, negative 10 combined with 3 is negative 7. And then multiply on the diagonal to get 1 times negative 7, which is negative 7. Then we combine down again to get 0, which is the remainder. And when the remainder is 0, it confirms that x minus 1 divides evenly into f of x and is therefore a factor of f of x. When that's the case, we want to pause with the synthetic division and continue with the factoring process. Remember, the goal is to factor this polynomial so that we can find the zeros. Our factor of x plus 5 is just copy-pasted down, but now we know that x minus 1 is also a factor. When we divided x minus 1 into this 3rd degree polynomial up here, the quotient is going to be the other factor, or what remains once we divide out that x minus 1. Here are the coefficients of that quotient. The quotient is going to be degree 2. So this 2 is going to be the leading coefficient on the x squared term. 3 is going to be the coefficient on the x term, and minus 7 is going to be the constant. Let's come back up to our steps for just a moment to notice step 5, that we continue with this process until we come down to a quotient that's quadratic. Sometimes that quadratic quotient can be factored on its own, and we don't need the P over Q list or the graph to help us to do that. We now have a quadratic quotient here, but unfortunately this quadratic does not factor using our AC method. So let's recall, in order to find the zeros of a polynomial, we plug in y is equal to 0 and solve for x. It's much easier to solve that equation when the polynomial is completely factored. And we do that by setting each of the factors equal to 0. Solving for x in these first two equations give us the zeros that we've already confirmed, but we're going to get 2 more zeros by solving this quadratic equation. Since it doesn't factor, we're going to throw it into the quadratic formula, which yields negative 3 plus or minus the square root of 9 plus 56 all over 4, which is negative 3 plus or minus the square root of 65 all over 4, and we're now ready to clearly state our answer. We did end up with 4 zeros. X is equal to -5, x is equal to +1, and x is equal to -3 plus or minus rad 65s all over 4. 4 zeros on a 4th degree polynomial function. But notice only these two were rational. Rad 65 is an irrational number. Therefore, this was not in the P over Q list.